Okay, we're going to recap some of the days we had that we missed to start things off. Hope everyone's doing great. So, this is for the homework that was due, technically 25 minutes ago. So, if anything, this is going to be the homework review. So, had a few people send me emails. I'm sure other people had questions. So, some of the first questions had to do with resonance structures. Now, resonance structures are a way of keeping track of molecules that just don't fit our normal ideas of octet rules and modes. We'll talk more about the octet rule exceptions. But here is a picture of ozone. It is O3. And when you draw its Lewis structure, here's one way you could do it. Notice there's a double bond and a single bond. But we could additionally choose to put the double bond over here. Now, we've sort of looked at this in a way saying, hey, these are isomers, but these are not isomers. So if we have the same exact connections, the only thing we're doing is changing where the electrons are found. So here we have an example of resonance. Now, if you think of hitting a bell and the metal just reverberates and vibrates, that ringing sound, that's also resonance. So here the idea is these extra electrons are partially shared across the entire thing, and our Lewis model just can't exactly tell us what it should look like. And so the real structure is a hybrid of the two. So if you could take these together and mold them, you would get not a single bond and a double bond, but kind of like a 1.5 bond across all three oxygen atoms. Now, carbonate, if you drew a Lewis structure, you could do this. You have one carbon with double bonded to oxygen, and then two that are single bonds. We did this one in class last week. Now, we know from bond lengths that if there's one double bond, its bond should be shorter, and the single bonds, they should be longer. But however, if we actually measure these bonds, which we can do with X-ray crystallography, we find that instead all of the bonds are exactly the same. So there's not a -2 here and a -2 there. It's as if the negative charge is distributed across the whole thing. So we say these resonance structures are individual contributors to the actual structure, where Lewis theory just doesn't quite cut it for molecules with what we call resonance. So another example, here's nitrate. So you might get started by drawing 3 bonds to 3 oxygens. And so now there's one extra electron that could bond. And we're saying that, well, you could make a double bond on the left, but also on the right and also down low. So in reality, it's as if it's all 3. So not one of these is technically the correct structure. So none of these actually exist. These are not isomers, so they don't exist by themselves. Instead, we think of it more like a hybrid. So here, nitrogen has that positive charge, but these extra electrons, this symbol right here, that is partial. They're partially negative charged. So we can kind of think of this like a rhinoceros. So a rhinoceros, it has a hard exterior like that of a dragon. It's got a horn on its head, technically, and like the unicorn. Now, neither the unicorn or the dragon actually exist. However, they contribute those properties to something like a rhinoceros. I know people love dragons and unicorns. I don't think people share the same love for rhinoceri. I think that's why they're endangered. That's kind of beside the point. But none of these actually exist on their own, just like these don't. But together, they represent this something here that in itself that has this extra 1.5 bonding character. So that's resonance. It's kind of a complicated topic that if you really want to better understand it, take some college chemistry and we'll talk about it there. Now, next on the homework, there were some questions about exceptions to the octet rule. Now, so these are generally pretty simple. We know all of them, the elements, they would like to have an octet, but just sometimes it doesn't work out. So first we have the incomplete octet. So take, for example, boron. Now, it only has 3 valence electrons, so it can only make 3 bonds. And so if you were to count up the number of electrons associated, we have 2, 4, 6. And that is not quite an octet. So you only get to share with what you actually bring. So boron has an incomplete octet. It has a whole orbital that's just completely empty. And there's just no way it's going to achieve that octet. Next, we have the odd electron. So everything always ends up pairing up, unless if you count up the valence electrons on the atoms and you get an odd number. There's no way you can take a nitrogen and oxygen and make everything pair up, since the total number, nitrogen has 5, oxygen has 6, it adds up to 11. So these are metastable, meaning they don't last very long. Actually, most people know them by another name. They're said to be free radicals, which is commonly a marketing term, which, I mean, it's a real thing, but it's these are molecules that would non-specifically oxidize, and that's kind of what makes them hazardous. They want to steal an electron because it doesn't like being on its own. And so a marketing term you sometimes hear is, oh, buy this product, it's got antioxidants. And so antioxidants prevent free radical damage, blah, 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 because they kind of throw themselves at the free radical and say, take my electrons, so that it doesn't take it from your proteins or DNA, and that's generally a good thing. And then finally, the most common is the expanded octet. So sulfur, generally you would say, has 2 bonds. It's going to have 2 unpaired two lone pairs, and then it's going to make 2 bonds to give it its octet. But sometimes here's 2, 4, 6, 8, 10, 12 electrons associated to that sulfur. Now, this only happens when you get down to period 3 elements and below. Again, so this occurs because once you get to the 3rd period, there's technically these 3D orbitals that can take part in sharing. This is live.
Live?
Yeah. Okay, I have an interruption. On the mic, here is Mr. Pate. Most of you would be expecting an interruption around this point anyway.
Absolutely. It's like, welcome to the light side. Try to move away from the dark side. Hope you're enjoying your break, but I'm sure that you would rather be here with Dr. Gleason and absolutely with myself.
Absolutely.
So stay safe. God bless.
Yeah. How many of them are actually going to listen to and watch these?
All of them.
Oh, good.
Yes.
So if you're listening to this already, kudos, pat yourself on the back, high five yourself.
If you're listening right now, you need to send Dr. Gleason a quick email with a timestamp on it.
Yep.
For 12:34-ish in the afternoon, and maybe he'll give you some extra credit points.
It's doubtful, but
hey, you never know until you ask.
That's true. Some of them do ask, though. Okay, with that aside, let's get back to the expanded octet. So we have sulfurs in period 3, and it has d orbitals. And so things like sulfur and phosphorus and chlorine, they form many of the polyatomic ions that we've talked about. So here's again a look on this. You can find this in the notes. This section I've highlighted in blue, those are the ones you're most likely to find this expanded octet. So carbon, nitrogen, oxygen, fluorine, they don't have d orbitals. They can't do this. But think of these d orbitals as like vacant desks, which I'm sitting in my classroom. There's a whole lot of them right now. They're all empty. But because these d orbitals are there, they can do more bonding than the normal 8 that we normally refer to. So sulfate, you won't have to draw this Lewis structure. But in sulfate, it has 2, 4, 6, 8, 10, 12 electrons associated to it. That's more than an octet. That's why it's called expanded. Phosphate has 5. 1, 2, 3, 4, 5. Chlorate has this one also has 5, but you can go up to perchlorate, which has 7. And so once you get up to these ones, you can find other covalent structures that have more than 8. But again, it has to be where there's elements that also have d orbitals. And in the 1st period and 2nd period, there are no d orbitals, not till the 3rd. Okay, so this is going to bring us to Vesper Theory. So again, many of you already asked questions and sent things on the homework, and I gave you awesome YouTube tutorial links, but now I thought I should probably do it myself. So Vesper Theory, valence shell electron pair repulsion, is a way we're going to looking at instead of just two-dimensional structures, how can we know how they actually exist better in three-dimensional? Because everything's in three dimensions, even though we might draw them in two. So the name kind of tells you what's going on. There's these valence shell electron pairs, and they repel. And so that's any electrostatic repulsions between all bonding and non-bonding pairs. And so I told you you need to be drawing the dots. Now I've looked at some of your homework. Not everyone drew the dots, and that's shame on you. Draw the dots, because here's where they're going to come up. So they don't actually take part in holding atoms together, but they're going to cause this repulsion that gives them different shapes. So we get the shapes looking at how the maximum number of electron pairs repel. So ultimately, we're going to see, hey, water doesn't exist in this linear shape. It's going to be bent, and it's because of those extra dots that are causing that shape. So we're going to look at a series of classes. So this first one is just, what if you have two things bonded to a central atom and there are 0 non-bonding pairs? So not terribly exciting, but we have here beryllium chloride. So there's only two things, and if you could imagine each of these atoms pushing as far apart as they possibly can, they're going to push 180 degrees. And when that happens, you get what we call a linear structure. Now, we don't care about the number of bonds. So here we have carbon dioxide, and even though carbon has 4 bonds, we're only counting how many atoms are bonded. So just like the one above, as long as there's 2 things attached, they're going to spread out 180 degrees. So you count double and triple bonds, still there's just one electron pair that's pushing against all the others. So if the first with 2 things is linear, if you throw 3, again, imagine it being linear and you throw some extra bonds, well, then you get what's called trigonal planar. So with 3 things, they're going to push 120 degrees apart. That's the maximum they can go. And from geometry, you might know that planar means flat. So you're going to have 4 atoms all in a plane. And they form a triangle. That's why it's trigonal. It's trigonal and it's flat. It's trigonal planar. So again, here's BF3 with 3 things. Here's nitrate. Again, notice there's technically 4 bonds, but we don't care about how many bonds. We care about how many atoms. 1, 2, 3. Here's ethene. So each of these carbons has 1, 2, 3 things attached, and that's what makes it trigonal planar. If you add a 4th one, you get tetrahedral. So kind of weird, 109.5 degrees, but this one's by far the most important, because when we talk organic chemistry, carbon tends to form 4 bonds, and if they're all single, you get tetrahedral. So again, it's referring to that because a tetrahedron is a 4-sided shape. So on paper, if I were to say draw the Lewis structure, here's what it looks like. But that's not how it actually exists. Instead, if we consider, and these look like 90-degree angles, but how far could they actually push apart? We get 109.5. One of the homework questions asks about this. So sometimes you'll see these bold lines and dashed lines. What it's trying to convey and show is a 3-dimensional shape where the bold line is going out towards you, the dashed line is going away. So even though it looks like these bond angles are all different, they're all 109.5. This also gives rise to certain things. Like here we have dichloromethane. And if you look at these 2 structures, they look different. Like, well, here they're side by side and here they're on opposite sides. Well, if you were to actually mess around with the models, you would find they're actually the same thing. Okay, now let me try that. I can't. Slight interruption. Okay, so here's my webcam. So here is methane. and it's tetrahedral. Those are my fingers. That's weird. Sorry, it's the first time I'm doing this. So I'm gonna put one on. Here's a fluorine. This is fluoromethane. It's still tetrahedral because there's 1, 2, 3, 4 things attached. Now I'm going to put 2 fluorines on there. And in the notes, again, if you looked at it this way, here was one of them where it looks like they're straight across, or you could rotate it this way, and here's where it shows them side by side. Either way, they're exactly the same thing. That's auto-focusing right there. Okay, now for a break. You're listening to Frozen 2 soundtrack, by the way, in case if that's picking up. Okay. Now back to notes. You go away. There we go. So again, these are not isomers. They're exactly the same. Now, again, here's phosphate. It has 5 bonds, 1, 2, 3, 4, 5, but we don't care about that there's 5 bonds. There's 4 individual atoms attached, and that is why it is tetrahedral. Now, I put an orange box here. Hopefully you remember. That means you don't have to study it. There are other Vesper structures, Vesper geometries, more than those ones. But here's a few you don't have to know. So phosphorus with 5 things attached, it spreads out in a trigonal bipyramidal fashion. Or here is sulfur hexafluoride, which we mentioned both of these have an incomplete octet. Now, the reason you don't have to, I have the orange box. I'm not going to ask you about these ones. These ones have that exception. They're not nearly as common. So of the ones we've covered, you need to know linear, trigonal planar, tetrahedral, but you don't need to know these last 2. Again, so here's just some other fun facts. Ooh, we'd watch this video. You still can about thalidomide. We talked about isomers last week and said one kind of weird isomer is the optical isomer. And what makes them weird is they look exactly the same. However, they have very different properties. They're just mirror images of one another. So here is meth. You might find someone on the news got busted, or those university professors in Arkansas that got busted for making it. But then here's also meth. But you can buy this stuff in the store. It's a nasal decongestant. It doesn't have the psychoactive effects. Again, the only thing different, dashed bold. So it different 3-dimensional mirror image, but it has very different effects. Again, if you watch this link, here's an even sadder example of that, where there's this drug they gave for morning sickness for pregnant women, and you can read it or watch it and just be sad. So 3-dimensional structure matters. Now, what all of these have in common is we don't have any of those extra dots, no lone pairs. So now what we're going to do is look at, well, what if there are extra lone pairs? So here's the ones we've seen, no lone pairs, but in red, here's ammonia, here's water. We're going to consider those non-bonding electrons as they don't take up space, but they are going to play a role. So again, going back to water, we see it, we've said it already, it's bent, but it's because they have these non-bonding electrons. So they even actually push with more electrical space than the bonded. So all 3 of these have a tetrahedral arrangement in terms of their electrons. Carbon has 4 bonds. Nitrogen has 3 atoms attached, but there's also a lone pair. Water has 2. Well, oxygen only has 2 things attached, but there's 2 lone pairs. So since they all have 4 electron pairs, whether bonding or non-bonding, they all spread out. They all spread out in a tetrahedral. But we're only concerned with where the atoms are. So we wouldn't call water tetrahedral. We call it bent if we're only looking at where the nuclei are. So back to the fun chart. So with 3 things attached, we would normally say, yep, that's trigonal planar. However, if one of them happens to be a non-bonding pair, if we're only focused on where the atoms lie and not necessarily the lone pair, we call that bent. So if this lone pair wasn't there, it would be linear. These would want to spread out 120 degrees. But having that non-bonding there pushes them so that it's bent. With 4 things, we would say it's tetrahedral. So 4 things. But if 3 of them are bonds and 1 is a non-bonding pair, again, we're only focused. So this non-bonding pair pushes these other 3 atoms down, and we get what's called trigonal pyramidal. Now, we already had trigonal planar, so 3 things bonded and it's flat. But with a non-bonding pair, it pushes these atoms further to one side. So ammonia, NH3, is trigonal pyramidal. It makes a tiny little nice pyramid. If you have 2 things that are bonded and 2 things that are non-bonding pairs, again, if we're only focusing here, so those other non-bonding pairs push them to the side, again, we get bent. So if there's 2 things attached, whether it's 1 or 2 non-bonding pairs, it would still be considered bent. And this is a really important one, because water, well, if water wasn't bent, it wouldn't have nearly the same properties. Its boiling point would be much, 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 much lower, and it would not exist as a liquid. Essentially, if all the water were to become linear at the same time, it would instantly vaporize and would probably all be dead, where we would have never existed in the first place. So these extra non-bonding pairs, they're really important. And then, similar to the others, here are some other fun facts you don't have to know. Distorted tetrahedron, T-shaped, linear, but with 3 non-bonding pairs. And again, these are only going to come up in kind of more obscure examples. Square pyramidal, square planar, you do not have to know. So in this larger table, again, you're only looking at these ones. So the rest of them make up a much smaller quantity. Here's where we would watch a video, but we're not going to. There's a link if you want to, because I bet you won't. Prove me wrong. So here is kind of what we're looking for. So on your homework, I got probably the most number of emails about people having questions when I asked you to tell me 2 geometries. So the first sum only had 1, but as soon as you start linking more and more atoms together, any atom that has more than 2 things attached, you can cite a geometry for it. So this table is probably the best one to review that I have in my notes. So notice if there's 2 things bonded to a central atom, it's either linear or bent. And so then to answer which one is it, what are the number of lone pairs attached? 0, 1, or 2. So if you look at this structure, find an atom that has 2 things attached. Okay, we have that, let's see, here, and we have that here. Okay, well, which one has 0 non-bonding pairs? And that would be these. So this carbon-carbon triple bond, both of these atoms would be linear. So from here to here, and here to here, 180 degrees. But the ones over here, whether they have 1 or 2 non-bonding pairs, it has a bent configuration. Those extra dots push them to one side. Then if the atom has 3 things, it's either trigonal planar or trigonal pyramidal. Again, we're not counting how many bonds, we're counting how many bonded atoms. So if we look at these carbons, they're trigonal planar because they have 1, 2, 3 things attached, no lone pairs. But then if we look at this nitrogen, 1, 2, 3 things attached, but this one non-bonding pair makes it trigonal. So then finally we have tetrahedral. So there's 2 carbons that have a tetrahedral arrangement where there's 1, 2, 3, 4 things attached, and that one's the same. So again, on your homework, where it says, what are the 2 geometries? The first thing you need to know is, well, what's the Lewis structure? And it says you don't have to actually draw it out, but here's nitrate. Actually, that's nitrite. But when we look at the fact that there's 2 things attached and 1 non-bonding pair, it's going to make it bent. Here we have hydrogen cyanide. We have 2 things attached and no non-bonding pairs. That's going to be linear. Here we have sulfur difluoride. Again, we might draw a Lewis structure where it looks nice and straight, but considering those non-bonding pairs push the fluorines to one side, it is going to be bent. Now, I wouldn't expect you to draw the Lewis structure of chlorate, but here it is. It's got an expanded octet. And with 3 things attached, we know it's going to be trigonal. But with an extra non-bonding pair, instead of trigonal planar, it's trigonal pyramidal. Again, here's formaldehyde. With 3 things and no non-bonding pairs, it's trigonal planar. And similar to your homework, here's one that has 2. Carbon's tetrahedral. and oxygen is bent. So here's another way we could show. So here's a Lewis structure, but then here's one where we're showing that three-dimensional space. Here's where we would watch another video, but we're not going to. Okay, so this actually brings us to the end of where that homework is. And so what I want to do now, something, is look at. Okay, so now that we're at the homework, again, kind of as a recap, we want to know what are some of the answers. So if you want something with a covalent or ionic bond, it really just has to be some ionic compound that happens to also have a polyatomic ion. So that could be something like sodium hydroxide, it could be calcium carbonate, it could be ammonium chlorate. There's a ton of them. So the polyatomic ion has covalent bonds holding it together. Like here's carbonate, while between the ions is the ionic. Resonance. So we're saying how many resonance structures? There's 3 for carbonate, because you could put the double bond here, or you could put the double bond on there, either and switch the number of electrons. And again, the important thing to understand with resonance is that the bonds are actually equal. Like it's to look at number 3, we're going to say they're a hybrid. That's a misspelling. A hybrid of each other. So together, all 3 of these are the same. And so the carbon-oxygen bond lengths are actually equal. There's not a shorter double and a 2 longer singles. They're all equal. We talked about expanded and incomplete and odd electron octets. And so if you look at chlorate and count up 2, 4, 6, 8, 10, 12, it has an expanded octet. And that's an exception. If you look on BF3, it only has 6. This is what's called an incomplete octet. And if you look at the hydroxyl radical, because oxygen and hydrogen plus the 1 electron only add up to 7 electrons, it's not going to be able to achieve an octet. And so it's an odd number electron. And so, again, we said those are really reactive. They're free radicals, and they're going to try to take electrons. So then we moved on to Vesper, which most of you should already have that. Valence shell electron shell repulsion. And it tells us the geometry, so that when we look at this stuff, there's a thing, SIBR4. Here we have, again, 4 things attached. And if there's no non-bonding pairs, then with 4 things attached, it's going to be tetrahedral, 109.5 degrees. Focus. Why are you being weird? Hold on. Click. Maybe that'll be better. It'll be 109.5. Now, so that one's tetrahedral. Then we have acetylene. So here's what the Lewis structure or the 3-dimensional model looks like. And so each one of these with 2 things attached, 2 and 2, that makes it linear. Now, if there was other non-bonding pairs, they would push and make it bent, but it doesn't have them. So it's not. Ooh, pink. IB3 or BI3. So here we go. So we have 3 things attached. There are no non-bonding pairs, so it spreads out 120 degrees. And this is what's called as trigonal planar. Again, it looks like a triangle. Yep. And it's flat. See how flat that is? Then we have SH2. So this is what we would call bent. Where's a bent one? Hold it. I got one. Look, it's bent. So if you have 2 things attached and 2 non-bonding pairs, so you could imagine there's these extra non-bonding pairs, they are pushing these other 2 atoms apart. So instead of being linear, they're pushed to one side. So H2S with two things attached to there and two non-bonding pairs, that is bent. Okay, then we have pH3. So we already had trigonal planar, but now we also have this extra non-bonding pair, and that non-bonding pair pushes. So when it pushes, again, here we see a phosphorus, 3 hydrogens, and this little guy, it's representing that non-bonding pair. And so instead of being planar, it's pyramidal. We got this third axis coming into play. So trigonal planar, trigonal pyramidal when it has a non-bonding pair. Moving down. Okay, so now we have, again, these are the ones I probably got the most questions on. CH4S. So you need to draw a Lewis structure, or you probably should. And then when you do that, you'll see that the carbon, this carbon right there, that carbon has 4 things attached, making it tetrahedral. But if you look at the sulfur, the sulfur has these 2, okay, now the alligators are non-bonding pairs. These 2 non-bonding pairs, they push, and so instead of being linear, it's bent. Okay, now we have pH3O, and I don't have a model of that, so let's just draw that. So again, as we would normally do, no, I don't want that color. Phosphorus has 5, oxygen has 6, make at least 1 bond. We have 3 hydrogens, and there is 1, 2, 3. So great, no double bonds needed. So 1, 2, 3. So we have this. So if we look at phosphorus, there is 3 things attached, 1, 2, 3, and 1 non-bonding pair. So if this wasn't here, it'd be trigonal planar. But because it is, it's trigonal pyramidal. Now, looking at the OH, it has 1, 2 things attached. Even though there's all this thing right here, we're still counting all of this as 1. So 1, 2. So 2 things attached, it's going to be either linear or bent. But because we have these non-bonding pairs which push them to the side, it's going to be bent on the oxygen. Green. Okay, let's do another Lewis structure. Okay, so we got carbon, we got nitrogen, has 5. There's got to be 1 bond. And do you see that plus sign? That means we get to take away 1 electron, and so that nitrogen is going to get an extra bond. Now, there's only 2 hydrogens, so that means we're going to need a double bond. So double bond, I'm just going to cross those out. We still have to make up for it. Triple bond, you go away. So now with our 2 hydrogens, there's 1, there's 1. So here is the Lewis structure. And if we look, each one of them has 2 things attached. And there are 0 non-bonding pairs. So with 2 things attached and no non-bonding pairs, it is linear. Both of them are linear. And then finally, we have this question about ibuprofen. And so with ibuprofen, we see that it has these dashed arrows. And what we want to know is what's up with those dashed arrows. So what they're doing is they're telling us about 3-dimensional structure, even if we're drawing it in 2 dimensions. So again, here are 2 things. These are optical isomers, also known as chiral molecules. And if you were to write out a formula, it'd be exactly the same. If you were to draw a picture in 2 dimensions, they'd be exactly the same. I mean, they look pretty much the same, but when you line them up, they're mirror images. I hit the box. They're mirror images of one another. There's no 2 ways you could superimpose them on one another. And so they technically would have different properties. So when you use ibuprofen, you're technically getting half of it. Only 50% of it is active. The other 50% just doesn't do anything, and that's okay. It's not that particular isomer is not toxic or anything. You just take it and be fine. Okay, so that was fun. I hope you enjoyed this, and in the future, I don't know. We'll just keep trying and see how these things go. How does this sound? I wonder what that looked like. So I'm in my classroom. I'm all by myself. I'm just kind of playing right now. Oh, that one was lame. Okay, have a good day. Yeah. Goodbye. Goodbye. Goodbye.